Good afternoon, everyone. I am Sulikta, and today I'll be talking about breaking the valley degeneration of excitons by proximity effect from ferroelectric substrate. And my system is transition metal dichalcogenide. So excitons are correlated electron-hole pair. So these quasi-particles form when you shine light on a material. So in transition metal dichalcogenide, the low energy excitons are doubly degenerate, and they are arising from K and K prime values. So these are also known as valley excitons, and these valley excitons shows an interesting property that they couple to circularly polarized light, but with the opposite helicity. So the K valley exciton coupled to left circularly polarized light, and the K prime valley exciton coupled to right circularly polarized light. So this means one can address and control these two excitonic states by changing the light polarization. So we can think of these two excitons as two states, Sk and Sk prime, and as any two-level system, we can form a linear superposition of these two states, and these linear superpositions will encode the linear superposition just corresponds to coherent superpositions of these valley excitons, and they can be manipulated by polarized light. Thus, these valley excitons can provide a natural platform for encoding quantum information, where these Sk and Sk prime excitons are served as these valley basis for the qubits. So far so good. But there's a problem. These Sk and Sk prime excitons, they are not perfectly isolated system. So they mix by, or they couple by exchange interaction of the electron-hole pair, and also phonon enables inter-valley scattering. So even if I initialize a state at a particular combination, the state can quickly lose its coherence, and this happens typically on a picosecond time scale. So this is not good for applications. So one way to circumvent this is to engineer a new level or new basis from these two states, preferably with an energy separation which can suppress this decoherence mechanism. So our goal is that to manipulate these valley excitons in a new alternative basis which can suppress some of these decoherence. And we can do that by subjecting this TMD layer in a spatially varying superlattice potential, and we can do that by putting this TMD layer on top of a ferroelectric substrate with alternating polarization domain. And a controlled way to generate this alternating polarization domain is if we stack two layers of HBN on top of each other with a small twist angle close to 0 degree. So we theoretically explore excitons in this setup, and this work has been done in collaboration with Professor Felipe Jornada from Stanford University. So first I am showing the top layer of a twisted bilayer HBN, in which we have different stackings. In this AS stacking, we have top layer which is just on top of the bottom layer. So this stacking has mirror symmetry, and it does not have any dipole moment. But if we slide the top layer with respect to the bottom layer, we get to this Bernal AB stacking, in which the top boron is displaced and now is on top of a hollow of the hexagon. So this has dipole moment, let's say along the positive z direction, and we also have this BS stacking which is just opposite of AB, and it has dipole moment along the negative z direction. So now in this twisted HBN, the stacking are continuously varying from AA to AB to BA, and as a result, the dipole moment is also spatially varying, giving rise to a spatially varying polarization potential. Now, if we stack a TMD on top of it, the TMD is going to see this polarization potential arising from the twisted HBN underneath. So here I am plotting the polarization potential felt by the TMD layer. The large red and blue triangle represents the stable domains of AB and the BA, and this thin line is the domain 1 region. And the potential changes sign is this domain 1, so there is a huge electric field which also propagates to this TMD layer on top of it. So because of this twisted HBN, the TMD layer is going to see a spatially varying polarization potential and the corresponding electric field. So now we are going to study exciton in this setup. So we study exciton by solving the Bethe-Solviter equation within the many-body conservation theory. So this first term represents the kinetic energy of the constituent electron and hole. The second term is the Coulomb interaction, the direct Coulomb interaction between the electron and hole cloud, and this is responsible for the binding energy of the exciton. And the last term is the exchange interaction between the electron and the hole pair, and is responsible for fine structure of exciton depending on its spin. So back to the TMD HB heterostructure, and this is the resulting absorption spectrum. Here we see the usual A peak and B peak. We are going to focus on this A peak region and plot an exciton corresponding to that. So exciton is a two particle wave function. So to plot an excitonic wave function, we fix the hole and we plot the electronic amplitude associated with it. And we do that for multiple hole positions. And here, in this case, we find that when we fix the hole at the domain 1 region, we find a large electronic amplitude. But if we fix the hole at some other position, the electronic amplitude is negligible. So this means that this exciton is confined in the domain 1 region. So this is a quasi 1D confined exciton, and on top of that, this electron and hole are tightly bound. So this is a quasi 1D 1-year exciton. We zoom further into this energy region and we see multiple excitons are contributing to it. So here I am plotting the oscillator state, which signifies like how strongly the exciton coupled with light. So there are many bright excitons with some energy split, which gives rise to this first peak. And we check their polarization, and they show linear polarization with orthogonal direction. So why does this happen? So to understand this, let us revisit the pristine excitons briefly. So in pristine TMD at zero center of mass, where we can optically access the excitons are degenerate and they couple to circularly polarized light. But at finite view, these valley excitons combine to form a valley antibonding combination and a valley bonding combination. So here I am showing the exciton dispersion. The orange parabolic line corresponds to the valley antibonding one, and this green line corresponds to the valley bonding one. At any Q point, the energy separation between these two branches are solely driven by the extent interaction of the exciton. And furthermore, these excitons couple to linearly polarized light. So now we have this electrostatic potential at the domain 1. The excitons are localized at the domain 1, which will correspond to a start potential for the exciton. And in presence of this potential, these excitons from the multiple Q points are going to fold in at the zero center of mass momentum. And because of these excitons from multiple Q points and two different branches are going to fold in, there is an energy opening at the zero center of mass momentum, and we find two excitons coming from these two different branches. So we recognize the lower energy one to be valley antibonding exciton, which couple to transversely polarized light, and the higher energy exciton to the valley bonding one, which couple to longitudinally polarized light. And on top of this, there is an energy splitting of 3.1 millieV at zero center of mass momentum. So this is exciting because now we have two states which can be still optically accessed and selectively polarized or selectively excited with controlling the linear polarization of the light. So if we want to excite the lower energy one, we can use a transversely polarized light, or for the higher one, we have a longitudinally polarized light. So this platform provides us an alternate basis for qubit applications. So to summarize, we had these energetically degenerate valley excitons which can form a basis for qubit, but this suffers from the decoherence. So we wanted to engineer some new level from these two states which can have some energy split between them, and we did exactly that. The potential from the twisted HPN leads to these linearly combined excitons which also have an energy split between them, and by construction this new basis suppress decoherence, extent mediated decoherence. So this provides us a more robust level for two-level system for qubit applications. And for future direction, we still need to investigate the dynamics of these two new levels for its proper application. For example, it suppresses extent mediated decoherence, but what about the phonon mediated scattering? What about the lifetime of this confined exciton? And what is the decoherence time scale in this new system? And also I would like to explore some tunability of the confining potential of this exciton and their dynamics. Thank you for your attention.
One short question. So the extent of the exciton.
Yes.
So what's the size that you would say?
So this is a theoretical calculation. So this extent is determined by the domain wall of this. So it was about 2 nanometer from our study, but in experiment, typically they have multi-layer of HBA. So the electric field line propagates like this. So typically they see a slightly larger radius of this exciton.
And the 3 MeV, like, if I just try to compare the experiments, how confident are you on this?
Yes, so there are like now.
The reason I'm saying is that we see larger scale.
Yes, yeah, that would be, I'd be happy to chat with you. So there are a few experimental reports also already which see larger speed, and this actually particularly determined by this width of this potential. So we have tried. So for here, I have used like 170 milliev, but I have tried slightly larger, like 200 milliev, and that already gave me 5 milliev speed. But this is our like proper ab initio calculations without fitting any parameters. So this is the result I am quoting.
Okay, let's try to pick up an excellent talk. Last talk by Nihapumari.
Hello everyone, today I am going to talk my recent work Zero Mode of Non-Abelian Dirac Operator in Topologically Non-Trivial Band Insulator, and this is the outline of my talk where
Your microphone has to be a little adjusted if you are not able to hear you. Maybe you can. You have mobile in your pocket? Mobile? No. So I think you can turn off that microphone. This microphone? No, that's turn off that microphone. Okay.
hello, is it not audible?
No, it's not switch on. Can you switch on that? I think can you give it to me this one? It's not on. I think this is on.
Hello,
Battery has to be replaced before.
Hello.
Just say hello.
Hello. Caller one.
Is it okay if you can talk from here? Sorry for.
yeah, okay.
Stand here.
Wait. Then hand is sick.
It's a laser phone.
Okay.
But you have a battery? Can you check that?
Wait.
Hello, hello, yeah. So this is the outline of my talk where we are going to discuss a general tight binding Hamiltonian. If that Hamiltonian have a degeneracy point, then we can obtain a zero mode equation, and that zero mode equation is satisfied by the probability amplitude of the state. So for that we have considered a very general model Hamiltonian. In that model Hamiltonian, this is our model Hamiltonian where k is confined in the k has the two components, the kx and ky, and confined in the first Billiard zone. And here the dimension of the this Hamiltonian depend on spin or orbital degree of freedom. This could be n cross n. So we have this very general model, and here the eigenstate of this eigenbasis and the orbital are related with the UN type of transformation. So for that, the first we are going to discuss the zero mode of non-abelian Dirac operator. For that we have considered a very general quantum state, and that quantum state in a quantum adiabatic limit, the parallel transport condition gives us this zero mode equation. This is the first result of our paper, and this zero mode equation is satisfied by the probability amplitude of this wave function psi, and this here the this covariant derivative also satisfy this commutation relation. That commutation relation is known as Young-Mills commutation. Okay, Young-Mills commutation, and the action of the projection operator from here gives us this non-abelian Berry connection. This is our non-abelian Berry connection, which is obtained by operating this projection operator on this wave function psi and k. Now, this commutation algebra we have also seen in this Landau-Weber physics, where this is known as the Heisenberg-Wally equation. So further from that, that quantum state for the infinitesimal parameter, we have obtained this quantum non-abelian quantum geometric tensor, whose dimension in general that dimension could be n cross n, and we all know that quantum geometric tensor can be decomposed into symmetric and antisymmetric component, and this could this berry curvature could be related with the Okay, so the berry curvature is experimentally so can be seen connected with the. Am I audible?
Yes,
Okay, okay. Sorry. So now further moving with this quantum geometric tensor, we have obtained another important relation by demanding this the inequality relation from this quantum geometric tensor. This is also known as the trace condition, and the lower bound of this trace condition is also known as the ideal fractional charge insulator condition. And from this lower bound of trace condition, we have obtained a non-abelian generalization of the vortexability condition, and that further vortexability condition could be also we have obtained the zero mode equation from this vortexability condition also, and this vortexability condition gives us the self duality relation of this covariant derivative, which is this covariant derivative. Okay, so now we are going to solve the zero mode equation for the prototype two band model. Here this is the non-abelian Berry connection and Berry curvature. If the non-abelian Berry connection have only diagonal part, then we can decouple our zero mode equation for two band model in this form, and we can solve this using ansatz solution, where this component is given by theta function and the phi part can be obtained by solving the modified Poisson's equation in the momentum space. So now we are applying this method to these two models. The first is the BAZ model. Here we have obtained the Berry curvature, and this is the expression of the Berry curvature. And the second model we have taken the rhombohedral NL layer graphene. Here we can see that the Berry curvature is NL time amplified, which have been experimentally also observed that the Berry charge number is higher in this rhombohedral NL layer graphene. And further, this is the zero mode equation solution on this model, where this are the for upper band, this is for lower band, and this is the full solution of the wave function which we can obtain through the zero mode equation. And u plus and u minus are a known spinor which can be obtained by diagonalizing the Hamiltonian, and the C plus and C minus could be obtained by solving the zero mode equation. Thank you. Okay.
So you said that the Berry curvature is in multiples of n, right?
Yes, in the this for NL layer rhombohedral LN layer graphene, we solved this Berry curvature. Then there is NL time factor for the Berry curvature.
What is the number that you get?
So okay, so this is the analytical solution. So NL correspond to number of layer.
No, but NL is multiplied by a number, right? For example, I go
Okay, so these are the beta and these are the parameters. So, I didn't understand your
for
question.
example, for single layer graphene,
Okay.
I know the Berry curvature is pi,
Yeah.
and for bilayer it's 2 pi. So will that?
So okay, so for that case there will be extra NL factor. For the single layer the NL will be 1. So for higher layer we are thinking this will be multiplied, and further we are also checking this.
Nice. Okay, thank you.
Okay.
So there are no questions. Let's thank you for excellent talk.
Announcement is that started pouring, so students can have food just outside that part. And this gate is open on this side. Faculty members can walk towards the cafeteria, and everybody has umbrellas and bags. So you can everybody use that. One more small thing, we need to present a token of appreciation for the chair for maintaining the time perfectly well.